In Chapter 0, I talked about mathematical models for systems and using those models to predict a system's response. I also said that engineers always want to use the simplest possible model for a system. The simplest model for a system will usually be linear. Engineers love linear models. They're way easier to analyze than nonlinear models. In this video, I'll talk about linear system models and how they differ from nonlinear models. First, just a few reminders about systems, block diagrams, and mathematical models. A system performs a transformation, usually associated with conversion of energy from one type to another or transferring energy from one place to another. This transformation is often expressed graphically as a block diagram. The system takes some input from outside of the system, and the output is provided by the system back to us. We want a mathematical model for the transformation of the input to the output, which gives us the output as a function of the input. So to get the output for some specific input, we just plug the input into the mathematical relationship and solve the math. Engineers always want the simplest possible mathematical relationship that provides a good enough estimate of the output. We can never exactly model the output for all cases, so we expect some error and design the system accordingly. A linear relationship between the input and the output will usually be the simplest, so engineers tend to use linear models a lot. For a linear system, the relationship between the input and the output can be expressed graphically as a straight line that passes through the origin. If the input, x, is plotted on the horizontal axis and the output, y, is on the vertical axis, the graph will look like this. When x is equal to 0, y is equal to 0. The slope of the line is m, so every change of 1 in x changes y by an amount m. Mathematically, the equation of the line is y is equal to m times x. There are a couple of really beneficial things about linear systems. For one thing, linear systems have only one solution. So if I choose a value for x1, there's only one value of y that will satisfy the equation. So if x1 is the input, y1 is the only possible output. This means we can usually calculate the output from a linear system in a single step. One really important property of linear systems is that you can use an analysis approach called superposition on them. This means you can subdivide the input function into several individual functions that are easy to analyze. Then we solve several simple problems rather than one really difficult one. One criteria for a linear system is that the output is 0 when the input is 0. Sometimes, however, the line describing the linear system doesn't go through the origin. For example, consider this line that has a y-intercept of b. In this case, the governing equation is y is equal to m times x plus b, where b is now not 0. The solution to this problem is pretty simple. We just redefine where 0 is. 0 is a relatively arbitrary value. In the case of linear systems, we can choose an operating point, which is also called the equilibrium point, as a reference point for any analysis that we do. Then we define a new coordinate system, which has the operating point as its origin. Now let's revisit our spring demo from Chapter 0 to see how changing the operating point changes the model. In that demo, we had a spring attached to the ceiling, and we added washers to the spring and measured the corresponding displacements. We used 0 washers as our 0. We don't have to do that. I've now got 2 little washers on here. I'm going to claim that that amount of weight corresponds to 0 washers. That's my new operating condition. If that's the case, then I'm going to call this 0 height. Now I can change the weight relative to this given value of 0. If I remove one of the washers, the weight goes up. I get about positive 11 inches of displacement. Now I can go back to 0 by adding my second washer on. Addition of a third washer is positive 1 washer relative to my 0, and the spring goes down by about 11 inches from its previous value. So this data gives me a new model with this being taken to be 0. Now let's talk a little bit about nonlinear systems, why engineers don't like them, and how we go about pretending that a nonlinear system is linear. For nonlinear systems, a plot of the output versus the input will not be a straight line. This curve, for example, would be a nonlinear system. A big disadvantage of nonlinear systems is that they can have more than one solution. This means that for some input, there may be more than one output that satisfies the equation. So if I input a value x1 into this system, the system could give me any one of these three values as an output. This is bad news if I want this solution and the system decides to operate over here, because the system won't work the way I wanted it to. One example of a nonlinear system is this silly putty. A common characteristic of nonlinear systems is that their behavior changes based on the operating conditions. If I pull on the putty slowly, it stretches. However, if I pull on it quickly, it doesn't stretch. It snaps in two. So the system's behavior changes depending on the rate at which the force is applied. Next, we'll look at a more detailed example of why nonlinearities can create problems in engineering design. Infrared, or IR, proximity sensors are useful for measuring your distance from an object. The sensor emits an infrared signal, which reflects off the object and returns to the sensor. The sensor measures the elapsed time and outputs a corresponding voltage. This is a plot of a typical relationship between the output voltage and the distance from an object. Unfortunately, for any output voltage, there are two possible distances. If we use this to guide a robot to avoid an obstacle, we may not be sure how far we are from the object or even what direction we need to go to get away from the object. Since nonlinear systems are difficult to design, we try to pretend that our system is linear during the design and then use nonlinear analysis and test data to make sure that the system actually operates where we want it to. The process of pretending that our system is linear is called linearization. The approach consists of choosing a linear relationship that approximates the nonlinear function over some range. To do this, first choose an operating point for the model. The linear model will pass through the operating point and it'll be tangent to the curve representing the nonlinear relationship. It'll be relative to a coordinate system whose origin is at the operating point. Let's see how this relates to our IR sensor example. I can arbitrarily choose an appropriate operating point on the sensor's operating curve. Now, if I draw a line tangent to this point, I can use this line to estimate distance from the output voltage of the sensor. This will probably be okay as long as I don't move too far from the operating point. But if, for example, I get to the left side of the cusp of this curve, I'll definitely run into problems. That covers the basics of linear models, how they relate to the equation of a straight line, and some of the limitations of those types of models. These concepts are the basis of most engineering designs.